All right, so there's some math that we can do with the irreducible representations in character tables. And one of the most common things that we'll be doing when we're solving problems is multiplying different representations together. So sometimes this is shown as gamma 1 dotted with gamma 2, where gamma just represents any arbitrary Molekine symbol for a irreducible representation. Or it can just be written as, the two gammas next to one another, just like how two numbers next to one another can mean, or two variables next to one another can mean multiplication. So for example, you could do A2 times E. How do you do that? Well, you just take the dot product. So you're just going to, it's not really the dot product, it's just multiplying all the individual components, very similar to a dot product. So A1 is 1, 1, 1. So here it is, 1, 1, A2 dotted with E, A2 times with E. So A2 is 1, 1, negative 1. So there it is, 1, 1, negative 1. And E is 2, negative 1, 0, 2, negative 1, 0. So you're just taking the first component, 1, 1 times 2, 1 times negative 1, negative 1 times 0. So that ends up with 2, negative 1, 0. And then you look at the character table and you realize that, hey, the vector 2, negative 1, 0 is already an irreducible representation. That is what E is. So A2 times E is just equal to E, okay? A1 times E is also equal to E, because A1 is 1. A1 times A2 is equal to A2. A1 times A1 is A1. A1 times anything is the same thing back because it has ones across the board. Okay, so A2 times E is equal to E. Let's do another example. What if we do E times E? Okay, this one's a little bit more interesting. E times E, well, it's like E squared, so it's going to be 2 squared, 4, negative 1, squared is 1, and this should be 0 times 0. Sorry about that, guys, but here, let me just fix that so it's clear. This should be 0 squared, right? But anyway, same thing. 4, 1, 0 is your vector. Now you look at the character table and you're saying, well, there's no vector that equals 4, 1, and 0. So you have to decompose this. And so you have to figure out what combination of vectors equals 4, 1, and 0. This is what we call a reducible representation. Because we can reduce it, we can decompose it into a combination of vectors. It turns out that A1 plus A2 plus E equals 4, 1, 0. How do we get this? There is a formula that we're not going to go over in this course that allows you to reduce it, and you just plug it through. You apply this formula. It can take some time, but you'll always get the right answer if you do the arithmetic correctly. We're not going to cover it in here because I want to mostly do simple problems that don't force you to use this formula. But so what we're going to do instead is just use guess and check. Okay, so basically what you're asking is, what vectors add up to give 4, 1, 0? And you just have to kind of look at it for a while and try some different combinations out. And then you'll figure out that, in this case, A1 plus A2 plus E give you what you want, 4, 1, 0. So you can check that. We can write down what A1, A2, and E are. We add them all up. 1 plus 1 plus 2 is 4. 1 plus 1 plus negative 1 is 1. 1 plus negative 1 plus 0 is 0. So we got that. So that proves to us that, yeah, A1 plus A2 plus E equals 4, 1, 0. We can do some more practice on reducing representations using this guess and check method. So what about this one? 3, 3, and negative 1. The answer is A1 plus 2A2, okay? And so just so you can see how that works, how would we check this? Well, we'd write down A1, and then we'd write down A2, but multiply it by 2 times because we found out by guessing and checking it was 2 times. And then if you add these, you can get 3, 3, and negative 1. So A1 plus A2 does indeed give us what we started with, which was 3, 3, negative 1. So we'll just be using this guess and check method because, like I said, all the problems that I'm going to be designing, we're going to be doing, I'll make sure are pretty simple. So we don't spend a lot of time, doing a lot of heavy math.